right, so this mini lecture is going to look at how magnets or magnetic fields influence charged particles. And so it turns out that indeed magnetic fields, it was discovered that magnetic fields do in fact influence charged particles. They cause a force on charged particles under two conditions. And so to explore those conditions, I want you to imagine yourself on a 4-lane highway, right? So here you are on the highway. Here's the highway. 2-lane, 4-lane. I'm just going to draw 2 lanes. All right. If you are standing on that little white line on the highway, and you're just standing there in the middle of the highway, and cars are zooming by you, zooming by you, zooming by you, nothing really happens. As long as you're standing there stationary and the cars are not on their phones, the drivers are not on their phones or changing lanes, but as long as you're standing there stationary, nothing really happens. Similarly, if a charged particle, here, if this, instead of a 4-lane highway, was my my magnetic field, and a charged particle was just there stationary, I'll just make it a negative charge for purposes for today. My charged particle was just sitting there stationary in that magnetic field, then nothing would happen. So that's our first criteria, that for a magnetic field influence on a charged particle, the particle must be moving. And of course, moving, there's a velocity, right? All right. Now, I want you to continue to imagine yourself standing on that line between the traffic, and you start to walk. Well, will the traffic influence you if you walk different ways? Yeah. If we walk in the direction of the traffic, so either with the traffic or against the traffic, but in the same parallel direction, I can kind of walk through the highway without, again, nobody changing lanes or being on the phone. I can walk through the highway without too much to worry about. Nothing's going to happen to me. Similarly, if a charged particle is moving either in the same direction or the exact opposite direction of my magnetic field, it's not going to do anything. What do I have to do to actually be influenced by the cars? Well, I have to walk in some direction off parallel. I have to walk with a component of my motion. That one doesn't matter, but that one does. So, the particle's velocity has to have a component perpendicular to the magnetic field. So just like I would have to walk into the street, the particle would have to have a component perpendicular to that magnetic field. So it doesn't have to be purely perpendicular, but that component, there has to be a component perpendicular to the magnetic field. All right, so those are our 2 criteria. And it's the perpendicular field that matters. So I'm just going to kind of take this image. I'm going to draw it up here for a second. So this is my magnetic field. And this is my particle with some velocity v. The component of that velocity parallel to the field, no effect. It's as if I was walking along the yellow or the white line on the highway. But the component perpendicular to that field is affected. Feels a force. And thus the particle feels a force. So what is the important element? Well, if we consider an angle, this angle theta, between the field I don't know if you can hear that squeak. My board is really squeaked today. That angle becomes important for what the force that particle feels. All right, so the angle is going to be important. The more perpendicular that angle is, you might imagine, the larger the force. What else might have an effect? Well, the field. If I have a really strong field, it might feel a larger force. How fast it's going might feel a larger force. And the charge. So all those things. So I was giving you pauses to kind of think about that. So if I increase the field, I increase the force. If I increase the speed of the particle, I increase the force. And if I increase the charge on that particle, I also increase the force that I experience. And that angle is important. This leads to the relationship of the force, which is the charge times the speed times the strength of the magnetic field, all those things, times the sine of the angle. When the angle is 90 degrees, when I'm perpendicular to that field, then I get a really big force, maximum force. When I'm parallel, 0 degrees or 180 degrees, the sine of that angle is 0 and I get no force. So it's consistent with our behavior. Now we know that velocity and the magnetic field are both vectors. This mathematically equates to, this was the magnitude, the full equation equates to the charge, whatever that strength of that charge is, velocity cross with the magnetic field. And that might look familiar from our study of Physics 1 when we looked at torque. So this allows us to get this cross product, it allows us to get the direction that that force on that particle feels. That the force, the particle feels. That doesn't sound right, coming out of my mouth. And whenever we use a cross product, we use what's known as the right-hand rule. And doing the right-hand rule on my light board is very confusing, so I'm going to describe it because while I might use my right hand, you see it as my left hand. So I'm just going to describe it for you. The right-hand rule tells us in this usage that we put use our right hand, use your right hand. You put your fingers in the direction of the velocity. You curl your fingers through the angle to B. This is to the magnetic field. This is also described as putting your fingers in the direction of the magnetic field. So you would curl your fingers towards B or put your fingers in, so you put your fingers in the direction of V, you curl them towards B or you change their orientation to B, and your thumb points in the direction of F. Okay, so this is the right-hand rule. All right? And I think I've said this in all the videos I do when I introduce the right-hand rule. It's very important that you use your right hand. I did an entire exam in advanced mechanics, and I'm right-handed on my exam using my left hand. And my professor said he just cringed because he knew all of my directions were going to be wrong. Why he didn't come up and remind me, I don't know. I'd remind you if you were my class. All right. Lesson learned, however, so maybe it was good that he didn't. I've crazied it into my brain since. All right. So that gives our direction of the forces. Okay. All right, so we're going to do a really quick example using these new ideas that we've just developed in that example. It's a biological example, so as you've learned, and maybe if you've watched the videos that I do on optics, that I love neuroscience. I was trained as a neuroscientist in graduate school. And so I love this example because it talks about what's known as the action potential in our neurons, the communication that we use. And the beauty of it is just it's the most beautiful, the action potential is the most beautiful physiological process, in my opinion. And it's electricity. It tells us that, gosh, even our bodies are physics. So probably what attracted me to neuroscience in the first place is that it's all just physics. Okay, so let's get that example up on the board. All right, and what we want to look at is, I'm just going to leave that up for a moment. What is the maximum force an ion? So that's a charged particle. An ion field might be potassium, for example, that does cross the cell membrane. What is the magnitude, an estimate, we're going to use estimates, of the Earth's magnetic field, so the Earth has a magnetic field, on an ion crossing the cell membrane during an action potential? Assume the speed of the ion is 1 times 10 to the minus 2 meters per second. We're going to estimate the Earth's magnetic field at about 10 to the minus 4 Tesla, and then the charge on that ion, we're going to use kind of like the charge on an electron, which is 10 to the minus 19 Coulomb. Okay, so let's write down what we know. We're saying that the magnetic field of the Earth is 10 to the minus 4. I think I've already forgotten what I've written down. 10 to the minus 4th Tesla. The charge of the ion is 10 to the minus 16th Coulomb. And we're going to say that the speed of the ion is equal to 10 to the minus 2 meters per second. So just a use of what force does this ion feel. All right, so we want the maximum force. That maximum would occur when? Well, it's going to occur when the sine of the angle is 90 degrees, when it's perpendicular to the magnetic field. Sine of the angle, sine we know oscillates between -1 and +1. So when it's 1, the magnitude is going to be at its highest. So we are going to look at the magnitude of that force. We're only interested in magnitude in this example. Q times the velocity, or the speed in this case, because we know the direction already, times the magnetic field. Again, we are saying that they are perpendicular because we want that maximum. So given that, we can just use this equation. 10 to the minus 16 times 10 to the minus 2 times our field of 10 to the minus 4, and we get an approximate force of 10 to the minus 25 16 plus 6. 16, 17, 18, 19, 20, 21, 23. 10 to the minus 23. Should just be able to add those up. Newtons. All right? So, that's pretty small. Pretty small. But our ions do, as they cross the cell membrane, feel a small force on those ions. And actually, it's kind of thought that they might be related to migration, which is kind of a cool way to think about it. All right, so quick little example of how we look at magnetic fields, how we see forces on charged particles. Good job.